Assalamu alaikum. Today in this chapter we are going to discuss entity relationship modeling. As we already covered in the previous chapter, database model and model is one of the very important element in database design and very important data model. So here in this chapter we are going to go for the basic concept and definitions that are used in models, and the basic component of entities and relationships and their representations will be discussed in this chapter, and we will go with more deeper analysis of the graphic representation of relationship among the entities, and will show how these representation will help you to summarize the amount of information or data required to implement a good database design. As we have already discussed in the previous data model chapter that models make the basis of an diagram, and diagram are used to show the conceptual database as it is viewed by end user, because every user have a different view of database, and diagram represent conceptual database as viewed by or as seen by the end user. Now diagram represent the database main components that we already know: entities, attributes and relationships. As we already discussed what an entity is, that entity is an object that exists. So in database administration we can say that entity can be a single thing, person or place about which data can be collected. It can be a physical thing or it can have a conceptual existence. If we look at the physical existence of entity, the example is like a student. It is the physical existence example of entity. Okay, student is an example of entity. Similarly, now company is a conceptual existence of something or of an object about which information can be collected. That is also an example of entity. And we have learned that in modeling level, an entity actually refer to the entity set and not to single entity occurrence. Okay, now if we map entities in model, it will map to the table. So entity map to the table, not to a single row. Single row of the table is called entity occurrence, but entity by itself refers to the entity set, that is whole table. Okay, not to a one row of the table. And we have two different models, Chen model and Crowfoot model, where in both of them entity is represented by a rectangle with name of entity written inside this rectangle in a capital letters. Okay, and you should write it as a singular form, not plural form. Like if entity is a student, so we will write student, not students. Okay, then comes attribute. Attributes are the characteristics of entity or properties of the entity. Like if we consider student as an entity, the possible attributes of this entity student can be student name, student address, student email address, student phone number. Okay, so these are what attributes. Attributes are the characteristics of entities. Again we follow two different notations to represent attributes. If we are looking at Chen notation, then attributes are represented as oval connected to the entity rectangle with a line as shown over here, entity is a student, we write this entity inside a rectangle, and the attributes are written inside this oval shape, and it is connected to the entity with the line. And if we look at Crowfoot notation, again entity is written inside a rectangle, and then attributes are written down inside this rectangle, like here student last name, first name, initial, email, phone. Okay, so these are two different notations that are used to represent like entities and attribute. Now we have different type of attributes like required attributes and optional attribute. Now the difference between required and optional attribute is required, as its name suggests, must have a value, but optional attributes we can leave them empty. So optional attributes they can have a null value or empty, but required attribute must have some value, need to be right inside it. Okay, domain is the set of possible values for an attribute. Like we can consider our domain as an example, like grade. So grade can have a value from A to F, A, B, C, D, E, F, let's suppose. So this is the possible domain for the attribute grade, student grade, let's suppose. Another example of domain is like gender. So if attribute is a gender attribute consists of two possibilities, male or female. Another property is that attributes may share a domain. Like for example, if we have two entities, student and professor, so we have attribute student address, professor address, two different attribute for student and professor entity. Then student and professor address share the same domain of all possible addresses. Then comes identifier. Identifier can consist of one attribute or more than one attribute that uniquely identify each entity instance or each entity occurrence inside the table. Okay, like for example, student ID. Student ID is unique for each different student. We can take this attribute as the identifier for the student entity because it uniquely identify each occurrence of the student record or each occurrence of the student instance. Okay, so but we cannot take a name as a identifier because it is possible that there are more than two students that can have a same name. So identifier should be a such attribute that is unique throughout the table. Like entities, we know that in relational model what we do is entity will map to the table, and your attribute of the entity will be the fields in the table or a column in the table. So we will choose that field as an identifier whose value remain unique in all the records in that table. So like student ID or a customer ID, so these values are unique, so these can be used as the identifier. And in case of relational model, these identifier are called primary key of the table. Okay, we use term primary key. Primary key is the identifier which uniquely identify each entity and instance. Okay, these identifier can consist of one attribute or more attribute. So we call it composite identifier if primary key consists of more than one attribute. Okay, then we call it composite identifier. Like here we have an example for the entity class. Okay, and entity class have different attribute: class code, CRS code, class section, class time, room code, and prof num. Okay, these are the attributes of entity class. Okay, so we map entity class to this table, and all the attributes are the fields in the table. Field mean this is first field, second field, third, fourth, fifth, and sixth field. Now we have to choose the identifier for this table. Now what should be the possible identifier? Can course code be a identifier for this table? No, course code cannot be identifier for this table because it is repeating here. Account 211, 211, 211. So it does not uniquely identify each entity instance. Entity instance is one row in this table. One row of this table is what? Entity instance. So course code is not a useful identifier. Can we take room code as an identifier? No, room code cannot be taken as identifier because BUS 311 and BUS 311, it is repeated in two rows. So no, it is not a identifier. So class code, let's see, class code can be taken as an identifier. Yes, class code can be taken as an identifier or the primary key of this table because it is unique in all the rows of this table. It never repeat itself. Here it is 12, 13, 14, 15. It is increasing and it never repeat itself. So it uniquely identify each entity instance or each row. So class code is a valid identifier or the primary key for this table class. But if we assume that we don't have a class code over here and we have to choose a primary key for this table, then we can go for composite key, because composite key where we use more than one attribute as a primary key. So in that case we can say that okay, course code and class section, if we take these two attributes together, they are unique, so they will never repeat itself and they can work as a composite primary key. Composite primary key when primary key consists of more than one attribute. Like here, this is the composite primary key and this is the normal primary key. Ideally we should go for a single attribute as a primary key, but if single attribute does not exist, if let's suppose this column has been deleted from this table and now we have to choose a primary key, then in that case no single attribute work as a primary key, so we have to look for composite key. So composite key where more than one attribute work as a primary key. Okay, then we have simple attribute and composite attribute. Do not confuse it with composite key, but composite attribute are those attributes which can be further subdivided, not the key but attribute, a single attribute. Like we have a attribute address. Address can be further divided into, like okay, if I write here address, it can be further divided into city, street, postal code or zip code. So address is a composite attribute. It can be further subdivided into city, state, zip code, street, so that is a composite attribute. Simple attribute is that attribute which cannot be further subdivided, like age, sex, marital status. These are something that cannot be further subdivided. So this is a simple attribute. Okay, name is a composite attribute or a simple attribute. Name can be a composite attribute because name can be further subdivided into first name, last name, middle name. Okay, then we have single value attribute and multi-valued attribute. Single value attribute can have a single value and multi-valued attribute can have many values. Okay, an example of single value attribute is like you can have a single civil ID number. Okay, no one can have more than one civil ID number. Okay, that is a single value attribute. And multi-valued attribute, like a person can have, if degree is a attribute, a person can have more than one college degree at the same time. He has a bachelor, master, PhD, let's suppose. So degree if attribute, then we can consider degree as a multi-valued attribute because it can have many values. Okay, how like here in this example we show an entity car in Chen model and Crowfoot model, and this entity car has 4 attributes: car, vehicle identity number, model code, car year, and car color. Okay, now this car vehicle identity number, this attribute where attribute is underlined in Chen model, this show that this attribute is the primary key of this entity. Okay, primary key or identifier. How we can show primary key or identifier? We underline that attribute. And then here you can see in Chen model we have double line. All other attributes are connected with car through single line, but this attribute is connected with car through double line. So this double line show that car color is multi-value attribute. How car color can be multi-valued attribute? It is possible that we have a car which have different color on the roof and different color on the door, and inside color may be a different, so it is a multi-valued attribute. So how can we show that it is a multi-valued attribute? In Chen model we represent multi-valued attribute with double line, but there is no particular notation used in Crowfoot model to show the multi-valued attribute. It is written like normal attribute, but primary key is identified over here. We write here pk mean primary key, and we underline it over here in Crowfoot notation. If we have many-to-many relationship or multi-valued attribute, then we cannot implement them in a relational database management system, because in case of multi-valued attribute, by the intersection of any row and column, if you have a one cell, so as per RDBMS we should have a single value into it. But in case of multi-valued attribute like a car color, if this is a attribute, multi-valued attribute, we can have more than one values for car color, which is not allowed. So how can we solve this issue? First solution is you can create several new attribute for each of the original multi-valued attribute. Like here, we can see that we have a car and car color. Now instead of having a single attribute, we create several new attribute out of it: car top color, car trim color, and car body color. Now instead of having a single attribute, we divide it into 3 different attributes just to solve this problem of multi-valued attribute. Then in that case, in a intersection of single row and column, we will have only a single value in each cell. But it is possible that if we add another attribute over here, car logo color, okay, we can add it over here, but there are some attributes for which we will not have any value. So in that case there may be a lot of null values over there. So we have another solution for this problem. The second solution is create a new entity. Like your multi-valued attribute, instead of considering it as an attribute, you change that attribute as a entity. Okay, like here we have car separate entity, and car color, which was a multi-valued attribute, we change it to a new entity, and we have a relationship with the original entity as one-to-many relationship. And we can put over here color section, and here color section can be whatever, top or trim or roof, and then we can assign it a value. And if some color section does not have a color value, we will not be adding it, so we don't have a lot of null values also over there. Then we have another type of attributes, we call them derived attribute. Now derived attributes are not physically stored in the database, but these are the attributes for which their values may be calculated from other attributes. Like for example, if the attribute is employee age, so we don't need to store employee age in the database. Instead we can derive it by getting the difference between the current date and the employee date of birth. In chain notation model, we represent the derived attribute by dashed line. Like here, employee age, it is a derived attribute. And how can we represent that this is a derived attribute? We are connecting it with the entity through dashed line. But in Crowfoot notation, there is no particular way to represent a derived attribute. Now, whether we should store derived attribute physically in the database or not, it depends on the choice of the database administrator. Every approach has its own advantages and disadvantages. So the advantage of storing the value of derived attribute is that you don't need to calculate every time, so it saves CPU processing cycle. It's whenever value is required, it is readily available without calculation, so it saves data access time, and it is easily available and can be used to keep track of historical data. But the disadvantage, if you are not storing the advantages of not storing the value of derived attribute is it saves storage space, because you are not saving it, so it saves some space, and computation, because you are deriving it every time on the runtime. When you need it, you compute it, so it always produce current value. Then we have some disadvantages of storing and not storing. For storing the value of derived attributes, some of the disadvantages, we require constant maintenance to make sure that the value is current, especially in case if value is used in the calculation change. And if we are not storing it, then the disadvantage is that every time we need, we have to calculate it, so it use CPU processing cycle, and because value is not over there, we need to calculate it, so it increase data access time and add coding complexity to queries in order to calculate that value. Okay, relationship, as we know that we create relationship between entities which show the association between entities, and these entities are participating in this relationship, so we call them participant entities. And we already see it in the previous chapter that relationships are always bidirectional, it operate in both direction, and we can classify a relationship as one to many, one to one, or many to many. We have three different type of relationship. And why we need our relationship to be bidirectional? Because in order to classify relationship, classification of relationship is that decide whether this relation is one to one, one to many, or one to or many to many. For this we need this both side relationship information, or both direction relationship information, because only one side of the relationship, if it is known and other side is not known, then classification would be difficult. Then we come to know about two new terms with respect to relationship. One is connectivity of relationship, and the other is cardinality of relationship. Connectivity describe the relationship classification. Relationship classification, we know that it is one to one, one to many, or many to many. But cardinality is something new. Now we can define a cardinality as it show the minimum and maximum number of entity occurrences associated with one occurrence of the related entity. And this connectivity and cardinality is decided based upon the business rule. How can we come to know that what is the connectivity or what is the cardinality? This information is derived based on the business rules. Okay, here in this example we show both connectivity and cardinality. Now this one to many is the connectivity between the entity, professor, and class. Now how can we decide that it is one to many? Because if we look at both direction, relationship between them, we can say that each professor can take many classes and each class is taken by one professor. So it means it has one to many connectivity. Now this cardinality, these numbers are written over here, that is 1 1 and 1 4. Now this 1 4 show that each minimum 1 and maximum 4. So it shows that each professor can take minimum 1 class, but maximum he can take no more than 4 classes. Okay, so minimum and maximum occurrence of the entity class with respect to professor. And here we have 1 1. Minimum is 1, maximum is 1. Like each class is minimum taught by one professor and maximum also taught by one professor. Or in other words, we can say that each class entity occurrence is associated with one and only one entity occurrence in professor. Okay, then come existence dependence. It means that an entity is existence dependence to another entity if it can exist in the database only when it is associated with another related entity occurrence. Like we have entity employee and employee dependents. Okay, so employee claim dependent. Now employee is the entity and dependent is the entity. Now dependent is the entity whose existence depend on the employee. If employee does not exist, the dependent of employee cannot exist. Okay, so this is an example of existence dependence. And existence independent is like a strong entity or regular entity which can exist apart from one or more related entity. Like in the same example, employee is a strong entity. Its existence does not depend on the dependent. Okay, so we call them strong or regular entity as well. The entity which can exist apart from one or more related entities. And existence dependence entity is also called weak entity. Like existence independence entity is called a strong entity, but that entity which depend on another entity is called a weak entity. Okay, how to evaluate the relationship strength? Now in order to evaluate this relationship strength, this whole concept is based on how the primary key of related entity is defined. Like the primary key of one entity that is on one side, if it appear as a foreign key in the related entity, then it is a strong relationship. Like I can show you over here. Yes. Like here, car and car color, and they have one to many relationship. If you look for car entity, the primary key is car underscore VIN. And if you look at the primary key for car color, it has primary key that consists of two attributes. One is car selection, another one is car vehicle identity number or car VIN. Now car VIN is a primary key in this car entity, but here it is the part of the primary key of car color and we call it a foreign key. If the primary key of one table appear in another table or in another entity, then it is called a foreign key. So car vehicle identity number is a foreign key over here, and it is the part of the primary key of car color entity. Now car is the parent entity and car color is the child entity. Okay, and they have a strong relationship between each other if the primary key of the parent entity is a part of the primary key of the child entity. Okay, and whenever we have one to many relationship, then the entity on one side, its primary key is a part is a become the foreign key on the many side entity. So same here. Okay, we have a weak relationship exist if primary key of related entity does not contain primary key component of the parent entity. Like here we have an example. We have course and class that have one to many relationship with each other. Course primary key is course code and primary key of class is class code. Course code is the foreign key here in the class entity, but it is just a foreign key. It is not part of the primary key of class. Primary key of class is only one attribute, that is class code. So this represent a weak relationship between course and class, that course code is not part of the primary key of the many side entity class. Okay, the same example here. Now course and class, here they have a strong relationship. Now how this relationship become a strong relationship, you can see that here in the course side primary key is course code. On the class side primary key is now composite primary key, that is course code and class section. So now the primary key of course is not only the foreign key of class, but it also become the part of the primary key of the class. So now course and class have a strong relationship. So this is the difference between strong and weak relationship. Okay, then we have weak entities. Okay, weak entities has to meet two requirements or two conditions. First condition is that the entity is existence dependent, which means that it cannot exist without the entity with which it has a relationship. And the second condition is that entity has a primary key that is partially or totally derived from the parent entity in the relationship. Like here in this example, employee has dependent. Like in Chen model, if a entity is a weak entity, we represent it with double rectangles. Okay, so dependent is the weak entity because its existence dependence depend on the existence of employee. If employee does not exist, his dependent will also not exist. Okay, so first condition met. Now second condition is that primary key is partially or totally derived from the parent entity. Now parent entity is employee, its primary key is employee number, and dependent entity has a primary key employee number and dependent number. So employee number, which was the primary key of employee, and here it is the part of the primary key of the dependent. So dependent is the weak entity. Okay, in Crowfoot notation, how can we show weak entity? There is no particular representation over here, but here you can see that primary key, foreign key, both. Employee number is a foreign key in dependent table and it also part of primary key. Okay, now if you can see that cardinality and of both, like here an employee can have a 0 dependent or n number of dependent, and each dependent has maximum one employee, belong to maximum or minimum one employee. So if you look at cardinality shown in Chen model and Crowfoot model, it is opposite. Here they show here 0 and n this side and 1 1 this side. Like dependent minimum 1, maximum 1, and employee can have 0 dependent or maximum n dependent. But in Crowfoot notation, these are on opposite side. So you need to be careful about it. Whether you are using Chen model or Crowfoot model, cardinalities should be shown in the proper way. Okay, and connectivity is one to many, one to many. But if we look at the relationship status, okay, dependent is a weak entity, but it has a strong relationship with employee. We just seen before the definition of strong relationship. Strong relationship mean that the primary key of dependent contain the part of the primary key of employee table, that is employee num. Employee num is not only the foreign key in the dependent table, but it also is the part of the primary key of the dependent. So dependent is a weak key, but it has a strong relationship with entity employee. So we can say that a weak entity in a strong relationship. Like here they just show because entities, when we map them to the relational model, each entity will change to a table or map to a table. So here we have an employee table, here we have a dependent table. And you can look at the field in these table. Field is what? Column. Each column in the table is field. Employee table has how many field? 1, 2, 3, 4, 5, 6. Dependent has 1, 2, 3, 4. Primary key of employee table is employee num. Dependent table primary key is employee num and department num, dependent num. And employee num is not the part of the primary key of dependent, but also is the foreign key over here. What is a foreign key? Foreign key mean if a field in a table is a primary key in another table, then it become a foreign key in that table. So employee num is a foreign key in the dependent table as well as part of the primary key of the dependent table. And dependent table primary key consists of two attributes, so it has a composite primary key because employee num and dependent num. Okay, a relationship participation can be optional or mandatory. If it is optional, it means one entity occurrence does not require corresponding entity occurrence in a particular relationship. And mandatory mean the opposite of it, that one entity occurrence require corresponding entity occurrence in a particular relationship. Like here we shown it over here through cardinality. Like 0 to n. 0 mean it is optional. So 0 or many. So the many side is optional. But if it is written like here in Crowfoot notation, you put it like 0 here. And if it is 1 and then this, it mean 1 to many. And if it is 1, it mean it is mandatory. Many side is mandatory. And if it is shown like two double line, it is having a cardinality 1 to 1 and one side is mandatory. But if it is written like this way in Crowfoot notation, cardinality is 0 to 1, so it shows that one side is optional. Okay, here we show the course entity and class entity, and they have a relationship generate and they have one to many relationship. But in this side, in upper side, it has optional. Many side is optional, 0 to n. It is possible that there is a course exist, but it is not offered in this semester, so it doesn't have any class. Okay, so 0 to n. But in this second diagram, it shows that many side is mandatory because here we have 1 to n. Okay, many side is mandatory, one side is mandatory. But in upper diagram, here one side is mandatory but many side is optional because it is 0. Then comes relationship degree, which shows the number of entities that are participating in a given relationship. So we can have a relationship degree as a unary, binary and ternary. Unary mean only a single entity is in a relationship with itself. Binary mean there are two entities that are in a relationship, and ternary mean three entities are associated in a relationship. Here we have an example like employee manages employee. This is an example of unary relationship. Like HOD is an employee and all other faculty is also an employee. So employee manages employee, or a manager employee manager. Like manager manages the employee, so manager is also employee and all other employees are also normal employees. So this is a unary relationship, an example. Okay, here we have an example of binary relationship, like professor teaches class. So there are two entities that are in this relationship, associated with this relationship, teaches. Okay, and then we have an example of ternary relationship. Now ternary relationship here, doctor prescribe drugs to patients. Now prescribe is the relationship, and there are three entities which are associated with this relationship. So we call it as a ternary relationship in conceptual form. But if we are going to write it in a logical form, then it can be written like this, like doctor write prescription, patients receive prescription, and drugs appears in prescription. So we can always convert ternary relationship into a new entity, prescription. We change this ternary relationship prescribe as a entity over here, and we can change it to like a binary relationship. So whenever usually we do not encounter ternary relationship, we most of the time in practical example deals with binary relationships. But if we have a ternary relationship in our ER model, then we cannot implement ternary relationship. So we always need to change it to binary relationship, as it is being shown over here, that this relationship prescribe will change to the entity prescription, and then we associate this entity with all of the other three entity into one to many relationship. Like doctor can write 0 or more prescription, patient can receive 0 or more prescription, and there are each prescription drugs appear in 0 or more prescription. So here we change this side as like 0 or more, or 0 or many, and all other are in the relationship of 1 to many. When we map this ternary relationship in the table form, this ternary relationship into the table form, we will get 4 tables: one for doctor, one for drug, one for prescription, and one for patient. Okay, and as we know that they are one to many relationship with prescription, so in prescription table the primary key of doctor, primary key of drug, and primary key of patient will appear as a foreign key. Like here we can see that primary key of drug is drug code, primary key of doctor is doctor ID, and primary key of patient is patient number. But if we look at the prescription, it have doctor ID, patient number, and drug code, all three of the primary key of these table as a foreign key over here. Okay, recursive relationships is the one in which a relationship can exist between occurrence of the same entity set. Like we have seen unary relationships. So unary relationships are recursive relationship. Like here we have this one to many relationship between employee, that is employee manages employee. So an employee may manage many employees, and each employee is managed by one employee. So this is what a unary relationship as well as a recursive relationship. Okay, another example here shown in this table, that is a unary relationship. Part contains part. Like it is possible there is a one part that consists of other parts, so part contain part. Now here if you look in this table, this part rotor assembly contain many other parts. Like you can see that part code for rotor assembly is C130, and you can see here in this last attribute part of part, it means rotor assembly contain this part, that is 2.5 centimeter washer and 1.0 mm rim. Okay, it rotor assembly contain this part, rotor assembly contain this cotter pin and copper part, and all other parts. So in that situation, if a part can be used to assemble several different kind of other parts, and that part itself composed of many parts, then two tables are required to implement this part contain part relationship. One table is not enough, so we need to break down this table into two tables as shown over here. Like we have now component table and part table. So now you can see that here this rotor assembly has part code C130, and this C130 component, C130 is the component now in this component table, and in this component table that we have a part code for all the parts that are used to create rotor assembly. You can add here component code with it, and it's more good way to manage this information as compared to the previous table. Okay, here is an example of unary relationship, that is one to many relationship, like one employee manages many employee. So this can be implemented with the single table. Here we have employee code and employee manager, like employee 101, who is the manager of this employee, 102, okay, and so on. But 102 employee does not have any manager, he is the manager by himself, so employee manager field is empty for this particular employee. Okay, many to many relationships are valid type of relationship at the conceptual level, and they are found frequently when we are doing ER modeling process. But when we are implementing many to many relationship, especially in the relational model, then it need the use of an additional entity which we call as associative entity. Okay, so the ER model uses associative entity to represent many to many relationship between two or more entities. Sometimes this association entity is also called as a bridge entity or composite entity, and this bridge entity or composite entity is in one to many relationship with the parent entity, and it has a primary key which consists of the attribute of each of the parent entity. Like here we can say that we have an example, student and class. Student enrolls class. This is many to many relationship. Now in order to implement this many to many relationship, we need a bridge entity or associative entity. So the associative entity will be this relationship between both of them, that is enrolls. Okay, so enroll here. Now how we will implement this many to many relationship? We will create a composite entity or associative or bridge entity between student and class entity, and we give it the same name as this relationship between them. Okay, enroll. And then student entity have a primary key as a student number, class have a primary key class code, but enroll will have a primary key as the primary key of both student and class. That class code and student number is not only foreign key in the enroll table but also is the primary key here, and we change this many to many relationship into one to many form. So on this side, both side, it is many to many, but it is connected with the other side, class and student, in the one form. So we cannot have many to many relationship in actual implementation. When we are going to change ER model into relational table, then we have to change this many to many relationship into one to many relationship by using a composite entity or associative entity. And when we map it into the table, it will look like this. Okay, student table have a student num as a primary key, and class has a class code as primary key, and enroll table will have class code and student num as a primary key, which both are not only foreign key but also the composite primary key of enroll table. Okay, now we have seen all the different concept of ER modeling. So now we will go through a case study where we will develop an ER diagram, but based on our knowledge about ER modeling, we know that database design is an iterative process. It's not like you have to go through once and you finish with your design, but you might have to go back and add more processes or object or attribute in your existing model. So it's an iterative process, and it consists of these activities where we start with creating a detailed description of organization operations, and then based on that you have to identify business rules. Then by using the business rules, we need to find out the entities and relationship between those entities, and when we have identified entities and relationship, based on that we can develop our initial ER diagram, and then we have to identify attributes for the entities, and then from the attributes we have to choose the primary keys that have a characteristic of uniquely identifying each entity instance. And once you have ER diagram, you can revise and review it. So whenever you revise and review it, new things can be added or an existing things can be removed. From this slide onward, case study about tiny college administration is given as a case study. They just choose a tiny college administration and how it works and how different activities are going on in this college, and based on that ER diagram is draw for it. So you can go through this case study and then corresponding ER diagram from the book. It is already given over here in the slide, but description of the operation is given over there in the book. So I would suggest you all to go through it from the book, and you will come to know that this is the overall UML diagram. Before that they used Crowfoot notation. Okay, what are the challenges or conflicting goals that database design need to be faced? The first thing is database designer must make design compromises because the goals are sometimes conflicting. Like they may have to adhere to the database design standards, because the database design must have to conform to these standards, and such standards guide you in developing a logical structure that minimize data redundancy, and then there will be a less chance of destructive data anomalies that can occur if we follow database design standards. So the next thing is processing speed. In those organizations that generate large amount of data or a large number of transactions, then high processing speed is a top priority in database design. And high processing speed mean minimal access time, and which may be achieved by either minimizing the number and complexity of logically desirable relationships. And third thing is information requirement, where timely information might be the focus of the database design, because if you need to make your decision based on your information from the database, then timely information is very important. Then we need a database design which should meet all logical requirements and design convention. and design is of little value unless or is of no use if it does not deliver all specified query and reporting requirement. Like, you make your design based on the business rule, and user requirement analysis is very important. So we need a design which deliver answer for all of our queries and produce the reports that are required to do daily day-to-day business. Because based on the design we perform implementation, but occasionally this can occur that you come up with the database design that does not produce a clean solution when you are going to implement it, but it occurs occasionally. So we have covered everything about ER diagram. Here, like, we have an example of implementation of one-to-one recursive relationship. And here which relationship, unary relationship we implement. It is unary because recursive. Employee is married to another employee, so this is the relationship, employee married to employee. Now here we show three different ways of implementing such a recursive one-to-one relationship. Like, we have in first solution we have a same table where we have employee number, employee last name, first name, and then employee spouse number. So employee spouse is representing the employee to which a particular employee is married. Then in the second implementation we divide it into two tables. One table is just for employee, another table is for married variant 1 we call it. And in second table, okay, first table is a clean table where we only keep the information about employees, and in the second table we keep information about the employee with employee spouse. Okay, then we have another solution for the same problem, that is the third implementation. Okay, now in this third implementation, instead of having two tables we have three tables. So we can see that based on ER diagram we can have different implementations, and different implementations have their own challenges and flaws, and based on that we can improve it and go back to the design and change it. Okay, here we have a summary. Thank you.